Well, we're returning back to looking at the subject of system design. Well, there are several reasons for doing system level design. I'll just read these really quickly, basically to find out if the problem is doable or tractable, to determine the performance limit of a design, to get good estimates of the cost, to reduce the risk of the design, to increase the reliability of the product, to reduce the overall cost, and to provide a framework for the organization and coordination of a team of engineers to work on the design. That probably, number 7, is the most important. Many of these are associated with working in industry. You as a student group, are going to march forth with this idea and not possibly throw it out as a company might do and start over. So let's take a look to see where we've been. We have just put together something called a requirement specification, and now you are doing a activity which is really not in the book here, which is taking that requirement spec and then translating it into a project application to get approval. Well, the book doesn't have that because the book doesn't necessarily require that type of a step. But what we're going to do here, this could be your project application or your requirement specification. The next step is to do the system design. Now, in that project application, I said your system design centered around a block diagram. But in general, if I bring up a pen here, in general, what we're really looking at is moving the Simulink idea right here at the system design level. So we'll change it now to what you are going to do for the next part. All right, and that feeds down into this as well. Okay, so the idea now is to move into this design where you're going to put this information into your proposal, and then that ends the course, and then you proceed on to 4820. 4820 is a very easy course, by the way. If you get everything set up in 4810, it's basically a breeze. All the suffering is done right now. So let's continue on with this idea. So we talked about a block diagram repeatedly, and this is an example having 5 blocks and kind of outlining how things are going to do. You should have this on your project application, so you can basically just discuss this, and it gives you something to talk about. The system design process is released again. Another diagram that kind of shows where we are starting here with the requirement specification or the project application and ending up with a detailed design on the bottom. So what's going to go on here is some thought process. You are going to come up with the concepts. This is the concepts for basically designing the system, all right? And you're going to take that and analyze it and synthesize a block diagram, essentially, okay? This idea here is essentially when you sit down at Simulink, and I got a blank screen. I gave you some examples to look at, but basically you're going to think about your concepts. You probably won't do too much analysis right off the bat. You'll throw something down here, and then you'll run it back and analyze that. You can either just look by visually, or you can run a simulation. Eventually you'll have some more things down here. We're going to show you a simulation here shortly. And then and then you'll be in this loop where you're constantly evaluating things. So you got the red concepts, the green analysis, and the blue synthesis. This will then give you the part of your proposal which is called the system design, okay? And the book calls it a system specification. So let's just kind of go over this really kind of quickly. The conceptualization, you're developing a hazy perception of the solution, rough ideas here. The synthesis is, the purpose of that is to create a well-defined structure for the concept. And the analysis part is the most important, actually. It's used to determine if the synthesized system will meet the performance and cost objectives. In other words, does it meet the specs? And depending on how well your system is modeled, you can actually get a pretty good idea how it's going. So in the analysis, you could be doing several of these things here, developing a mathematical model, simulating the system on using Simulink, and then you could even actually, like in the guitar example, lash together a laboratory version of the system with some components and see how well it works. So in this example, now this isn't a face-to-face meeting. I used this example, and earlier I didn't even have Simulink. So we were basically putting a block diagram for a simple modulator, and like only you people that are taking the 4000 level class can understand this. But basically, I'm translating a digital signal in red here to a modulated carrier, and then that goes off to the telephone line, and we can do some analysis here. But all this stuff now can be done in Simulink. I don't need to do a lot of the stuff that I was doing earlier. So anyway, in this example, the mixer's model as a multiplier, and we can do that in Simulink. We can measure the power X spectrum of the output. We can do that in Simulink. We can do all this. Everything can be done now. It's all automatic. What a change in what is now available. In the refinement phase, so that what I got done talking about is just an example of the conceptualization idea there. So in the refinement phase, the objective is to modify the synthesized concept based upon information gained through analysis. Analysis in your case is running the Simulink and seeing how it works. And then finally, you will document your results. This documentation, they say, is going into something called a systems specification document. In your case, it's going to go into your proposal. Okay, I don't think you've got time to put it into your project application, but the next phase is to write a proposal, which is almost the same as your project application, except it's got a schedule attached to it, plus it has any of your simulation results. So now it's come to the time to show you an example Simulink system design, and I'm going to show you a student design. Now this is going to be a pretty nice block diagram that I'm going to demo, and so look for this one in the file that I'm going to be sending to you. And then the students actually had a little write-up showing me how to run the system. It was quite a bit longer than this. I just picked out the essential parts here. So let's switch on over to Simulink and take a look at their design. Well, the first thing you'll see is there's 1, 2, 3, 4, 5 tabs in their design, and they came up with an initial block diagram, kind of a vague idea, and then they got into the nitty-gritty. The nitty-gritty here is if you press the input tab, and then you get the block that is shown. So this is Simulink, and so therefore, following those instructions. Okay, so if we just kind of go flying back to this. So what we're going to do here is look at the FSR input, and then we're going to look at the force curve block here. So the FSR input is over here, and you can see what they're doing. They've got this model. Again, this is very simple to do. What they did is they constructed a force versus resistance curve here, and then to go back, you hit the back arrow, and then the next thing that they said to do is go to the test block, all right, and then look at the FSR circuit. So we'll do that. And then you'll see the tremendous amount of real thought and organization that's done by these students that couldn't write the project application, really. Did a poor job on that. Had good writing skills, but bad organization though. So they came back and did amazing stuff here on the block diagram. And they were able to recoup their grade, actually, with this. So they're going to be talking about working with some sensors. Let's fly back here to this part here on this. So the sensors are going to be looking at the 16 sensors placed in this block here. And so you can see this if you, excuse me about that, if you double-click in this FSR force curve. And go ahead, let's double click there. And there, look at this. So they've got 16 sensors that are set up, and they're monitoring all of this. This is tremendous. This is a tremendous example. It's probably more detailed than most of you will be able to produce, but it gives you a real goal of what you can do with Simulink. And this runs too. So I want you to go ahead and look at this and run this program. It's going to generate a curve that will show, and this is done, where is it? It's done right here, and this curve is generated here. And it's part of the thing that they did. So this is an example, and it's within the scope of a student doing it, because I had 3 students do it, and they didn't do such a good job initially, but they came back strong on the system simulation. Okay, I'm going to end this talk here by talking a little bit about many of you are building a system based upon an idea of using a Arduino or something else as a controller. So really quickly, I want to tell you what the Arduino can do and then what's beyond that. All right. So the idea here is, and this is how MathWorks does their block diagram. So this basically is following the concept of the course. I thought it was an amazing slide here. So the requirements are the specs to your project, all right? And then you're going to do some research and design, which is the process of this course, and this is 4810. And you're going to prototype it with an Arduino, which is over here, or a Raspberry Pi, I guess if you prefer. And then you're going to eventually implement this and build this. And if you have a controller, it will generate code, and you can hard code the Arduino to do what you want. And it provides all these different languages that are done. Then you have to integrate this and test and verify. And this is all done in 4820. If this sounds like computer engineering, it is, but with Simulink, all this complexity and all this modeling is available now to the electrical engineers, who do not know all this vast detailed amount of information. So this is what is amazing, is we're really rapidly looking at integrating these 2 fields, and the electrical engineers can do some of the things that only computer engineers could do earlier. So real quickly now, the MATLAB and Simulink support the Arduino, and this is the MATLAB portion, and this is the Simulink portion. It's just kind of showing you that the software is available. By the way, I did I'm running this on a Macintosh, and in the version 2020B, the Mac is now fully, the Arduino is now fully supported, and earlier it was not in 2020. So this is due to the operating system that was changed on the Mac, and it had basically moved to a 32-bit operating system, and without any more support for the 16-bit operating system, 16-bit algorithms, and so that caused a problem and some chaos here with MathWorks software. So they fixed that on this latest version. So the idea here is to do your early prototyping on an Arduino, Raspberry Pi, etc. And then should you need to, and I've got, like for example, this semester in 4820, I've got one group here that really needs to move to a better board, okay, than the Arduino. But you can do your rapid prototyping, your student stuff over here, and then if you need more capability, you can buy these. These are $1,000 a piece probably, okay. So this example is actually showing how to handle the quadcopter orientation control. All right, and so it had a number of things that had to be done: interrupt-driven monitoring. This was a prototype that was built, and when they built this, they really found out that they tested it with an Arduino, and they really found out that it was not able to handle the complexity of this project. And so what they did here is they moved from the Arduino Mega to an STM Nucleo, all right? And that just had a lot more capability. So this is the idea here, what we're looking at. Isn't this a nice diagram? This is really kind of illustrating the idea of moving from one end to another. Now, for a student project, you probably will just stay in this area, although an Arduino Do is actually a much more higher performance system. It's an ARM processor, and it has, I think, about 3 to 4 times the clock speed. So let's take a look at the comparison of between these two boards here. So the more powerful in general may be needed for some certain projects. It gives you better synchronization, more processing power, and greater precision. And so let's take a look at this. This is really the part of the whole presentation of concerning the Arduino that I want to show you. So if you compare this ARM processor with the Arduino Mega, you can see that the Mega can only handle 1 interrupt at a time. Okay, but you may need something where you're handling multiple interrupts at a time. The processor is basically an 8-bit processor in the Mega. Well, this STM32 is 32, and then some other things associated with the precision. So basically that's it. The end of my presentation. It kind of gives you an idea of what to look for in 4820 should you need a more important, more powerful processor. And this will take care of it for today. So good luck on working on your project applications. I'll be looking forward to seeing that turned in this week.